Hi, I'm Oliver Gao. I'm the director of Cornell Systems Engineering Program, and I have been conducting these system conversations with our Ezra System Seminar speakers that we invite to our campus. Today, I'm very delighted and honored to have Dr. Denis Dochain, who is a professor at the Université Catholique de Louvain in Louvain-la-Neuve, Belgium, and he's also an honorary research director from the FNRS. In English, it's National Fund for Scientific Research. His main research interest covers the modeling, analysis, design, monitoring, and control of reaction systems. And I believe when we talk of reaction systems, there are so many different types of reaction systems. Dr. Dochain, it's very nice to have you today. So I was looking at your research record as well as your teaching record. It's really amazing, covering so many different fields, and it's apparently a very nice fit to our systems engineering view and also approach. I would love to learn more about yourself, your career, your research, whatever you would like to tell us about your systems research and life.
Well, I started my studies in electrical engineering, so I'm electrical engineering by diploma. But then very quickly at the end of, let's say, my electrical engineering studies, I started to work on, let's say, reaction system. But by that time it was anaerobic digestion for this, which is one of the standard wastewater treatment process.
Mm-hmm.
And then I studied my PhD on, let's say, biological systems.
From electrical engineering to biology.
So control of biology, modeling and control of biological system. And it was clearly a decision on my own by that time. And so it was probably very innovative, I guess, by that time. There were only a few people in the area of control that were active in biological system. So at some point, my PhD is on that topic, but then I quickly realized that biological systems are just one of the many cases of reaction system that we have in our applications, let's say. So going to chemical engineering was kind of natural at some point. Mm-hmm. And so I was very much involved in, let's say, chemical engineering. So I even got a position at the École Polytechnique of Montreal at the chemical engineering department. And when I went back to let's say, my university, I was also in charge of the chemical engineering studies for quite a while. So my connection, sometimes I say I'm a strange animal, let's say. Yes. On one side, I'm a control engineer with a background in electrical engineering, and I'm also, let's say, I have a strong flavor of chemical engineering. So I've been teaching also in chemical engineering courses for a long time. So at the same time, I have these both faces, and so this is probably one of my identity, let's say, today. Mm-hmm. But in both cases, in all cases, one of my, let's say, concern was to find out, let's say, the system engineering, let's say, basis of all I did. So I was trying to look all the time at reaction system as a system, let's say. And so to find out what is, let's say, the specific characteristic of any reaction system, and so what we can learn from that. So typically reaction system, all the models that we use have, let's say, specific features in their models. Then so in consequence you have a number of specific properties. Mm-hmm. So one of the typical properties that you have in any reaction system is the notion of reaction invariant, for instance, the fact that the reaction is a constraint in the dynamics of the system, at least for systems that are, let's say, closed, let's say, so without any interaction of the system. And then in that case you can find out that you have a real mathematical invariant, in the sense that part of the dynamics, let's say, are typically equal to 0 in that case. So this is one of a nice thing. So it was clearly one of my concerns. My concern is always to say, okay, try to look at, let's say, the most, specific and system engineering view of the reaction system, and to come up, let's say, with a view that can be generalized to any type of reaction system. And for me, this is was, for instance, it was very helpful at some point, because at some point I'd been contacted by the European Space Agency to be involved in a big project that they call MELISA, which is indeed aimed at making sure that the space stations are autonomous, and also autonomous in terms of food. And so they had what I call sometimes the space greenhouse project. How I say when I say it like that. So they want to grow food, let's say, on board. I mean, and I'm sure that NASA is the same type of project, let's say. So this is for the European Space Agency, and so my knowledge about, let's say, the potential of, let's say, the reaction system models was very helpful for me to come up with an appropriate strategy to come with, let's say, reliable model for plant growth at the same time. Really inspired for what I did in a biological system before. Because in the end, a plant is just another biological system, if you look at that.
That's true.
And so, but then of course there's a number of many different things. I mean, a plant is not a microorganism, if I may say it like that. No. So this is very specific with that respect. So so in simple words, I hope that I give you a good picture of what is my, let's say, background and where I come, and then where I go.
This is a very nice spectrum that is covered, by this systems approach, and also, of course, with a specific tool of control, right? You are trying to look at all these different systems, and you mentioned that, you at one point you made, you did your undergrad in electrical engineering at some point, and then you made a decision, and that was your own decision, to go for a PhD in biological engineering. So I was curious, because I think because for our program now we have a PhD in systems program. So we have a lot of students. They came to system engineering with different training and background. This is we call PhD in system. However, we have students with background and training in philosophy. We have students from economics, and we have students, of course, from the traditional engineering field. So when you made that decision to go from electrical engineering to biological engineering, that seems to be quite a stride. So what was your motivation?
Well, probably there's a number of, let's say, experience in my life, in my face like that pushed me to go in that direction. First of all, my father was a doctor, a medical doctor, and he used to be a scientist before starting his, let's say, medical doctor career. This is probably one of these. So I've probably been very sensitive to biological system from the very beginning. And then at some point, as a student, so I was, let's say, staying with people in agronomy, so what we call bioengineering today. So we have what we call that in the translation, let's say, in English, is a circles of students. So it's typically a bunch of people that live together, and they do, let's say, a number of activities for students related typically to one of the faculty. So that's what we have in Belgium. We don't have that everywhere, but this is very specific, at least in our university and in Belgium. And so for some reasons, let's say, at some point I had good friends into that, and they asked me to join them, and then I had a very close relationship with people in bioengineering by that time. And so this is probably the second, let's say, important experience that I had in terms of, wow, yes, I really would like to work on that. And so this is probably what was my motivation. And the last thing was very strange, because at some point, as an electrical engineering student, I wanted to work in electronics. But so in our system, we have to do what we call a final year work, which is typically after your work in the So we have 5 years engineering studies, only in the 5th year. And so one of the best students in, let's say, in our group came to me and said, I want to do it with you. And he said, and I want to do that in automatic control. And I said, oof. Okay, I like automatic control, but my first choice is electronics, and I had already one topic that was selected by me, and then I was accepted for that. And I say, okay, you want to do that with me in automatic control, great, but I select the topic. Mm-hmm. And there was one topic, say, related to anaerobic digestion. I say, we are going to do that. And so this is probably was the final step to go in that direction. And then I knew that, okay, so this is a number of, let's say, little things, let's say, in the end that makes your choice. I mean, they decide that you decide your choice. So this is really the, let's say, the starting point.
That's right. Kind of, we look back, it's really those consecutive tiny points, right? But I think there is something like kind of internal, as you mentioned. You have some interest, even though you started with electrical engineering. But however, your dad was doctor, and then you had some interest, and also it sounds like one key, tiny but critical thing was that microbial project that got you on the track, right? So with this, I think you talk about automatic control. Of course, you've been doing this control research, from wastewater treatment all the way, as you mentioned, to the plant in the space, right? So with these things, so far now, if you look at all these things as optimizer that is trying to work in this kind of automatic control, what's your view? What things we can control, and what things we cannot control, or can we control everything?
Can I respond differently to your question?
Please. Whatever way.
Very often I consider myself as a system theory people than more than automatic control guy. Mm-hmm. So I would say automatic control, or a control, let's say, is kind of a byproduct of my perspective in system theory. Because if you as you mentioned at the beginning, I mean, I've been working in modeling, analysis, whatsoever, design, monitoring, and control, I would say. And so control is important. But for me, my main motivation is to come to a better understanding. So if we understand, let's say, well, the dynamics of the system that we are dealing with, then we can do a lot. And do a lot is, of course, not just modeling, and modeling is important, but also then come with, let's say, monitoring, let's say, and also control. Okay, that's my idea.
That's great. I'm glad that you brought this up. You emphasize that actually your real interest, your emphasis is actually on system theory. That's a very good point, because I feel a lot of things, especially when we think about biology. I think if you think about system theory, and if you even push it further, I feel that will push people to think about system philosophy, right? Especially if you look at how biological system works, and versus how our engineered product works. And then in the end, in a society, there is an engineered product, there is biological entities, and in the end together, they form this society. Right, so in terms of system theory, and I agree with you, and you are pursuing a better understanding of the dynamics and the underlying driving factors of these dynamics. So, and I was reading, the abstract for today's work. You are talking about, biology, right? We're talking about, and I was impressed, and I agree with you. In this century, biology is the science, while in the past century you think it's physics. So now, how do you link biology and system theory, as you just mentioned? What is the linkage, and what is your view when we apply system theory to biology?
Well, probably I shall be more explicit in my seminar, but then I would say, it's like you have to consider, let's say, the biological system as a system. That's what just I want to say. Mm-hmm. And of course, the difficulty that we have with biological system, let's say, is twofold. If I simplify, these are very complex systems, and you are facing system with living organism, which is probably very different from any other type of systems. And so the challenge is to come with a system view on biological system that addresses these two issues. Okay. For instance, in terms of modeling, we know that a simple model will ever do a better job than a complex model. So how can we reconcile this, let's say, basic paradigm, let's say, and the reality of the complexity of the biological system? And that's where, for me, system theory is important, because then you know that we have to find out, let's say, what is the best option regarding, let's say, the objective that you want to follow with respect to what would you want to do with this specific biological system. Okay, that's in summary, this would be that.
So when we talk about biological systems, of course we can look at just one individual, and even at from the cell level to the organism and then to an individual, right? So I feel like one of the benefits of system engineering is that by looking at either the components or the components together from a holistic view, such that system engineering is very well suited towards addressing the emergent behavior, which means that if you just add all these different components together and it's actually their interactions, that is something that you do not expect when you just add them together simply. So this is what we mean by emergent behavior and the complexity. So that way, when I'm thinking, if you think of a very extreme case, like in our human society is consisting of individual biological systems. And of course, each individual has all different organs that are biological systems. So what do you view as the major challenge in dealing with these multi-scale biological systems? Because when you go from one scale to another scale, the features and the characteristics and even the tools to address them will be totally different.
I'm basically very ignorant with respect to the multiscale, let's say, dimension, let's say. It's still a challenge in my mind. But at least what I know is that, let's say, we have to look from the microscopic level to the macroscopic level. That's for sure. And so, for instance, we have been able to develop, let's say, fantastic tools in metabolic engineering in the large sense to better understand what is happening inside the cell. And these are tools that are really great today, and so it helps a lot to know what's happening on that side. But on the other side, there's an ecological dimension. What about the interaction of individuals? And individuals can be a cell from one cell to another. It's not individuals, let's say, like just persons. And so this is very important. So that's what I like to exhibit these two extreme dimensions. Yeah. Personally, I still don't know how to reconcile, let's say, these let's say, which call it in the end is a multiscale problem. At least I have good ideas how to address, let's say, the separate ones. Because, and I didn't mention that, but microbial ecology and ecology also is one of my, let's say, main research topic today.
That's wonderful, ecology. So speaking of ecology, I saw that actually, you teach a course where you say, societies, populations, environment, development, issues, and interdisciplinary approaches. I was looking at your website. That seemed to be. Do you want to talk a little bit about that course?
That's probably one of the most exciting courses that I ever taught in my career.
Wonderful. So I picked the right one. Yeah, because my own research area is actually looking at the transportation, air pollution, and the public health, kind of very related to this topic. That why I would like to learn more about. Yeah, this course.
So this course is part of a multidisciplinary education in our university. So it's after, let's say, the what we call the master degree. So it's 1 or 2 years, and so this course is the biggest course in this
It's a degree program
for this degree. And what is really exciting is that, say, there are different parts of this group, but the central part of this group is a play on role. And typically it's a public debate on a topic of interest in environment in the large sense. Okay, and so typically students are divided into groups, let's say, into roles, let's say, and so they prepare all along the semester. They prepare the debate. And then they come to the last Wednesday before Christmas, and so the full day is dedicated to the public debate. Okay, and so typically we have a number of topics. Let's say, for instance, last year we had a topic which is very hot today. Is the plastics in the oceans, but we have many of them. I mean, so we had the mining resources. It was the year before, if I remember. So, we are exhausting, let's say, the mining resources today. So, what are we doing in the future? What about how can we recycle? Make sure that we recycle, that we don't throw away, that we are able to make this recycle by separating the parts of any device, for instance, and so on. So this is, last year we had that on the plastic in the oceans. And so typically the roles that we had, of course, because it's organized by the United Nations, so the secretary is done by the United Nations, but we had different countries like the US, where you had indeed we selected to have the European Community. I can't remember which country we had also, maybe Russia. I'm not sure. Anyway, maybe China. Maybe I don't remember. I mean, I have to check. And then we have, let's say, Greenpeace, and then so you can understand we have, let's say, multiple actors that they have a complete different view on that. But then in the end, they are supposed to come up with some kind of agreement in the end. Yet they have to defend, let's say, their viewpoint. So that's very exciting, because they really start from the very first day that we tell them about the topic. Let's say the play on role, they really start, and so they start to have, let's say, of course we are coaching them. So we have regular, let's say, meetings to tell them, okay, so you should look at that, or maybe your position you should adapt it like that. Or maybe don't forget maybe to contact potential allies, or maybe to try to understand what are the views of your so-called enemies, let's say, if I may say it like that, and so that they can come up the day of the debates in a position that they can do their role, let's say, optimally, let's say. And so it's really fantastic. They're really fantastic, and the students, I mean, all the students that came on from these degrees, the best memory is from the display on role, because they really learn a lot. And so we are very lucky, because we have a true multidisciplinary view of that, because we have students from everywhere, from engineering to laws, and we have people from biology, from chemistry, from let's say, economics. And things like that. So it's a very large spectrum. So it's great, because we make sure that we have groups that we have mixed, let's say, disciplines.
That's really a very nice reflection, of providing system views into to the students, right? So I think this sounds like a very good course. Even be very nice to our system student. Right, so I'll follow up with you, kind of probably ask you for a syllabus. And
we don't have syllabus, but that personally, I strongly believe in, let's say, the positive aspects of the play on role. as long as if it's appropriate in your teaching, and you do it, let's say, in a way that is consistent, it's always a very good experience, because I do that in a completely different courses, which is called, let's say, technological risk, let's say. And so typically, I put the students, it's also a player who I put the students in a situation when there is an accident in a company typically, and they have to react. And so this is a complete different perspective, but then they learn more than from any course when they do that, because they say, oh yes, we have to react that way. Oh yes, we should know that we should do that at this time, and so on.
So it kind of, this is really nice. You're talking about technology risk. You're talking about kind of a pedagogical ways to teach the student, and also how you can innovate in teaching, right? That's actually something. This reminds me kind of because we, for any researcher, right? So our ultimate goal is to have impact, to have a positive impact on the society and to contribute to the society, while a lot of times researchers are thinking about publishing papers, however, and also teaching all these kind of technical analytical courses. But I can see that you are so excited about this course having the student playing a role, and I suspect probably in that course there is no equation.
Of course not.
Right. However, like you feel the impact to the students and even to the instructors, the impact is really significant. So this I think for us to...
You cannot imagine how much I learn and I learn every year from that course.
Yes. Yeah. So with that, so now, and also I feel like, because the topic you selected, those are the topics that are addressing a lot of challenges that our society is facing. So nowadays, right? So with this, so now coming back to, there is biological systems, and now here there is, and there is ecological system, and then there is this kind of social technical systems, right? So, and you've been working on all these different systems, but some modeling and analysis, and hope you always want to bring this system to a better place, right? But what are the key differences in terms of approaches that we can take in dealing with a biological plant versus dealing with an ecosystem, and then versus dealing with a social technical system like what you covered in this class? What are the key differences of the tools or the approaches?
Difficult question, I would say.
Yeah.
I don't know. I mean, I tried also to for me, my view is that I always try to spend a lot of time in listening. So, of course, for biological system, I didn't have any biology courses before I started to work on that. So I had to learn on my own. And so I learn a lot by listening. And it's probably something which is one of my, let's say, characteristics, is probably someone for whom it's very important to listen. And so I'll try to listen and then try to make, let's say, so organize, let's say, my thinking from listening, let's say. And so so then I see this, I see that, maybe these are the connections that I can make. But, it's not very formally, I would say. For me, listening is so important, and so that's why I learned. Mm-hmm. So if I go back, for instance, to the plant growth, at the beginning I was really lost. I had already more than 25 years experience in biological system by that time, and I realized that plant growth was such a new world for me. So it took me some time. I had to read a lot, I had to listen to all these plant growth people. So I tried to really, it took me some time to make the connection. And it's exactly the same when I look at this technological risk, or this kind of, let's say, this debate, this play on role, when, you have to listen to the people. And so when you capture, let's say, and make the connection, some connection with what you know, maybe you can come up with, let's say, proposals. But I don't know. I mean, apart from that, I shall be very modest, but I don't know. I don't know to address your question.
But I think you did. I think you did address my question. I think one thing is really, as you mentioned, right? You did not have the biological background in training. However, and you did great research in biological system modeling. And I think the one key thing is that I think you are a very adaptive learner by listening, right? I think that's actually, I think a lot of times people, and also sounds like to me, you have always been pushing yourself outside of your comfortable zone all the time.
That's so obvious with me.
Yes.
I mean, for me, my career was a number of opportunities, but then opportunities that were able to push me, outside, I say, my comfortable zone.
Mm-hmm.
It's exactly that. I wanted to be always learning something new, and this is really. I mean, I really enjoy to have so many challenges to face in my career. This is yes.
So that's why I always believe things that make a person successful, even though you don't realize, but there have got to be those things that are very consistent, that make you successful when you are 7 years old, that make you successful when you are 70 years old. There's something that is very consistent. It's not only kind of in the technical skill or technical ability, and also some kind of mentality. So now if you think back, what are, when you were facing challenges, and in the end you overcome the challenge, what were those kind of consistent factors that kind of helped you overcome one challenge after another one?
For me, I would call opportunities, and these can come from different sources, let's say. So when I ended up my let's say PhD, it was obvious that I had to find another niche, if I may say it like that. And so that's why I went in two directions at that time, and I say, okay, the first thing is that I realized that the biological system are just one case of reaction system, and the other part was more on the system theory side, because I realized that in many cases the system that I've been handling so far were described by ordinary differential equations, but indeed many of them were described by partial differential equation. And so in mathematics we are going in another world. We call that infinite dimensional system. And so that's why I started to work on that. Mm-hmm. And I say, okay, there is another challenge. There's a challenge in terms of, let's say, application, if I may say it like that, but there was a challenge in terms of theory. And so this is exactly that. For me, this is just a question of opportunity. Another opportunity dimension is the plant growth. I mean, these guys from European Space Agency, they came to me. But there's another opportunity which comes from, let's say, something that I had in mind since I was a student. As a student, and I'm probably a strange animal with respect to that, because most students hate thermodynamics. I was loving thermodynamics as a student. And so for quite a long time I was, let's say, wanting to try to find out how I can, let's say, incorporate thermodynamics in my system theory view. And so in system theory, I mean, all the stability theory is known as typically Lyapunov theory. And Lyapunov theory is often, let's say, identify, or let's say there is a formalism that shows that you can use energy functions, energy as let's say, a tool for finding out Lyapunov functions. So typically in electrical systems and also in mechanical systems, it's easy to find a quadratic function of the variable, which is an energy. Mm-hmm. And so then from that, it's an excellent candidate for Lyapunov functions. But you don't have that with reaction systems.
That's true.
because energy is not a quadratic function of the variables. And so what can we do? But on the other end, we have another of good properties of these systems. For instance, the variables are positive. Concentration, temperature, for instance, are positive variables. And so I realized that if I want to introduce energy in my, let's say, the conceptual view of the Lyapunov theory, I needed to include thermodynamics. And the opportunity for me was to have at some point a PhD student was really brilliant. And I said, you are going to work on thermo. Mm-hmm. And this was really my starting point. And today, I mean, it's one of my main topics. And I consider this as my last major challenge in my scientific career. Can we come up with a thermodynamics-based system theory, system and control theory? So can we design, for instance, controllers on the basis of thermodynamics function? Okay, like entropy or let's say entropy production. So we're already able to generate a number of very good ideas about that. But then there's still so much to do, because thermodynamics, from a theoretical point of view, is wow. I mean, when I started to work with, let's say, this what I call infinite dimensional system, I tend to say by that time it is infinitely more complicated than with finite dimension system. And I say thermodynamics is probably even more complicated, more complex. Mm-hmm. And so this is, but this, as I try to explain to you, this is just a question of opportunity once again.
Yes, speaking of this, this thermodynamics, of course, this, thermodynamics and the control, and coming back to your, this role-playing course in society's populations, I believe, from that course, people, students, and you talk a lot about, the current challenge that our society and the world is facing. Just let's not talk too far away. Just think about a city, right? If you think about a city, and then how, if you imagine use your thermodynamics, this theory, and also control, can we drive a city towards a direction that we believe is a better way?
So your idea is to connect, let's say, the notion of entropy and what's happening in a city. Is that what you have in mind?
That's right. Applying, because you can see that of course, we a lot of time we work on this engineering system. However, I believe as an engineer, especially now with all this monitoring and this data collection, imagine that if we can monitor the city, the city activities, including human and the organization, imagine we can monitor these activities at a very fine resolution, can we apply your system theory and through the modeling and tell decision makers that, maybe we can go this way towards better sustainability or better resilience. So instead of, because otherwise so far a lot of, how can we first model that, and how can we convey your recommendation to the decision makers?
Good question. Sorry to tell you that, but I never thought of that before. So it's I would say why not, and I don't know from let's say from which starting point we should go. I don't know, but why not? I mean, say okay.
Yeah, because that way you translate your research exactly into not a city, just the town, like in Louvain, right? If in Louvain, and then if in that, I think it's a small, middle-sized place, right? If I believe, it's a system dynamics, there's thermodynamics, all these things. Thinking of system dynamics of a town from a thermodynamics point of view, and they guided by your system theory.
Mm-hmm.
Yeah.
But you know what? I don't remember exactly what Albert Einstein did say, but so he had a nice, let's say, opinion about thermodynamics, and he was mentioning, let's say, the universal, let's say, feature of thermodynamics. So when you tell me that, I say, okay, why not why should not use thermodynamics for addressing this kind of societal issue? I don't know.
Yeah, I think that would be very powerful. Yeah,
why not? I don't
Yeah.
know. I don't know.
So-
And I say once again, I want to be very, very modest, and I'm not sure. Let's say I don't know enough in social science to tell you anything. I don't have. I cannot come with an expert opinion on that. I can be maybe a personal opinion, but and even then, I would say I would be very cautious. I don't say yes, thermodynamics can help you. I would say why not?
Yeah, a different perspective at least.
Why not? But then, okay, let's be. I want to remain modest. Let's say.
Oh yeah. So that's why I want to tell you, do not make that thermodynamics. That you said that you thought that was going to be your last scientific endeavor, but do not make that one the last one.
Of course not. No. But then, for me, it's such a big scientific challenge.
Yeah.
And I'm a level at my career, and I'm close to the end in some ways. Of course, probably I shall be a scientific researcher till my last day. But then, it's so big that I can spend the rest of my life, working also on that. Maybe also on other topics, but then also on that.
Maybe probably next year when you offer this course, a role play, you can consider adding some thermodynamics, some perspective. But I think we're running out of time. But I think this is great. I think it's really from your career and from your research. In the end, I think we talk about a little bit about these societal challenges. And I saw that in your talk, you are going to address a lot of the key challenges and the difficulty and also opportunities in this biological system. I think one thing I learned from this conversation, I think you probably didn't notice, when I asked you, how did you overcome the difficulties, the challenges, and your answer is that you view those things as opportunities. I think that's actually a very important, optimistic way of looking at things. So for a lot of people, they say, oh, this is so difficult, this is so challenging. But you see the other side of the coin. You say, oh, that's an opportunity. I think that's probably one of the things that have been kind of driving you from one opportunity to another opportunity. Thank you very much. I very, very much appreciate.
Thank you very much for inviting me, and it was a very pleasure to have this discussion with you.